Thank you, Nima. You're always very kind. As always, it's my pleasure to be here and to share with you what I know about the subject. I went through the list of you, of the participants, and checked out what you do, and it's amazing how broad the spectrum, how wide the spectrum of your expertise is. And unavoidably, therefore, there will be some of you who know everything that I'm talking about, some of you who have absolutely no clue, and unfortunately may not have a clue even after I gave my lecture. So especially to those, I encourage you, as Nima said, to come and talk to me. Now, the title that was assigned to me by the organizers is Standard Model Backgrounds at the LHC, and I put backgrounds here in parentheses for reasons that I will explain now in my first few slides. So, of course, we're talking about backgrounds to what? Backgrounds to BSM, beyond the Standard Model, to the discoveries, to supersymmetries, to, well, even the Higgs to some extent, even though it's a Standard Model process, but it's in the domain of objects to be discovered, which have been discovered. So the study of Standard Model backgrounds at the LHC relies on our general understanding of hard processes at the LHC. And this is not just something that we put to use when calculating backgrounds to new physics. It's something that we use to calculate signals as well, beyond the Standard Model manifestations, like production of gluons. And in general, the interpretation of the results that come out of the LHC has to rely on the tools that we use to calculate the background. So in that sense, it's a bit limiting to say, I'm going to tell you about the backgrounds, because to do that, what I will explain to you, in principle, you can apply it in any other domain of LHC physics. For example, measuring the top quark mass is a purely Standard Model endeavor, but the techniques that you use, the things that you need to know, then become absolutely essential if the day you discover the gluino, you want to go out and measure the gluino mass or the stop quark mass. We look for possible signals of new physics in the Higgs sector, strange Higgs decays, for example, or anomalies in the branching ratios of the Higgs. And when we look at branching ratios of the Higgs, we have to understand the Higgs production and decay mechanisms, because we are taking ratios in different channels. And to do that, even if there were absolutely no background, still we have to rely on an understanding and a modeling of the process. Kinematical distributions in general, if you want to extract, for example, the spin of the Higgs, you have to rely on knowledge, which is very basic properties of final states in hadronic in proton-proton interactions. So, as I said, it's not just an issue of Standard Model backgrounds, also because even if you just focus on pulling out BSM signals, it's not just by producing a BSM particle and detecting it that you can have evidence of BSM phenomena. So one has to be, again, a bit more open-minded in what he's looking for. For example, assessing whether the Higgs is Standard Model or not is not an issue of background. It's just a study of production and decay properties. If we have an anomalous source of missing transverse energy, I mean, we have events more than we would expect with missing ET. So we settled the issue of the backgrounds because we came to the conclusion that there is more than you would expect in the Standard Model. But then we will not know whether, it doesn't come with a passport times supersymmetry. We will have to prove that it's supersymmetry. A signal with multi-jets plus missing energy could easily be some say, fourth generation or sequential heavy quark that decays to W's and to jets, and the W's decay to leptons and missing energy. So at the beginning, it won't be possible to tell the difference. If we look at something like, you probably heard, I assume, of these anomaly seen at the Tevatron in the forward-backward asymmetry of top quarks being produced. The top quarks tend to be to go preferentially in the direction of a proton, while the anti-tops tend to go preferentially in the direction of the antiproton. This may seem like an intuitive thing, but the reality is that certainly at leading order in QCD, there should be absolutely no correlation between the direction of a proton and the direction of a final state quark, top quark. And the main reason is that either you produce top quarks by using glue going to TT bar, and the gluon doesn't care whether it's sitting in a proton or an antiproton, or it's a quark-antiquark annihilation, but the annihilation goes through a gluon. And once you have that gluon produced, again, the gluon doesn't care whether it's coming from a quark-antiquark or antiquark-quark. So there is absolutely no memory of initial state at leading order. So it's only higher order QCD corrections that induce a correlation between the directions. So it's a quantity sensitive to higher order corrections in QCD. And if you go out and you calculate in the standard model, you find a prediction for this production asymmetry that is short by a factor of 2 compared to what you find in the data. There is no reason to expect that this is a problem of background. The signal is very clear, very clean. Certainly not standard model background. One could argue that there is beyond the standard model background. So instead of just producing tops, one maybe is producing also stops, for instance, that then decay to tops, and that gives rise to some contribution to the asymmetries. So again, physics beyond the standard model manifests itself in many different ways, and therefore, to pull it out, it's a broader physics program than just considering backgrounds. Now, there is another reason why it's useful to talk about standard model in general, one considering the prospects for BSM physics at the LHC. And that is that with very few exceptions, whenever you produce a BSM particle, that immediately and unavoidably decays to lighter objects, which eventually turn out to be the lightest states in the standard model spectrum. In addition, perhaps, of course, there can be something like a WIMP, like a neutralino. If it's supersymmetric chain, there will also be the lightest supersymmetric particle which is left out, but typically that will not be visible. Everything else which is visible will be standard model. So all of the direct BSM searches rely typically on inclusive observables which are built out of standard model objects, leptons, jets, photons, and neutrinos. Now, jets is a generic word. Jet is, the evolution of a quark. And of course, whether it's an up quark or a down quark, or whether it's a B quark, jets can be different. So one can be a bit more sophisticated because today detectors are so good and the analysis techniques are so good that one could also intercept one of these unstable particles as it decays down to the stable objects that eventually the detectors will see. So one can reconstruct, for example, a W and a Z boson by looking at the decay products and uniquely identifying their source, their origin in a W or a Z boson. A tau lepton, for example, that also decays quite quickly, but it has signatures in the decay that allow us to reconstruct and group together a set of particles saying that's coming from a tau. Same for the charm, the bottom quarks, and even the top quarks, even though their decay modes are quite complicated, there is a lot of tracks and jets, but there are techniques in which one can tag a set of elements in the final state and say those are coming from a top. Typically, you would say they are coming with a given probability. So that means that we can define observables also out of unstable objects. So it's not just the electron, the muon, etc., but we can construct observables such as, for example, the PT of a Z boson in a final state or the PT of a B jet and use them in the study of the final states. But the result is that since every BSM particle goes to these, then BSM searches boil down to studies of the properties of standard model-like final states. So we're talking about W and Z plus jets, for instance, jets plus missing energy, TT bar associated production of top quarks, B quarks, and jets, associated production of pairs of W's and Z's and jets and so forth and so on. The other interesting, well, it's not interesting, but it's just a remark, is that even standard model processes have their own backgrounds. It's not just the BSM that has background. So take, for example, the production of a W, decay of a W to mu neutrino. It's PP going to W that goes to mu on neutrino. Well, you can generate those final states, for example, by producing a pair of charm quarks, CC bar. Of course, they will start emitting radiation, they will emit gluons, they will hadronize, they will do things, and then they will decay, and they could evolve in such a way that the momentum taken away by these radiated gluons is very small, so the charm at the end of the shower is still carrying most of the momentum of the jet. And then it can also decay in an asymmetric way, in which, for instance, the muon coming out from the charm decay takes away most of the momentum of the charm. And on the other side, the C bar can have exactly the same evolution, but instead of decaying to the muon carrying away most of the energy, decays to the neutrino carrying away most of the energy. So at the end, you will have a muon and neutrino plus some crap, some, small energy hadron. So you could argue that perhaps it's exactly the existence of these objects that will make these look different than this one. But unavoidably, also in this event, which was indeed a clean W, but the fact that the initial state is made out of quarks unavoidably will lead to the additional presence of other objects. So gluons now, they will not come, or extra quarks emitted from the initial state, they will not come from the evolution of a final state, they will come from the evolution of the initial state, but the bottom line is that the event looks exactly the same. And it all boils down to decide whether it's a signal, namely a W, or a background, namely a CC bar, all boils down to what is your resolution, and which scale are you willing to look at your process, to which extent are you willing to live with the presence of some additional components of a final state. And there is clearly a boundary between a clean, very likely W sample and a sample in which there could be some contamination. So this is one example, just also to introduce some terminology that's used typically in the experimental papers and in the experimental discussions. Let's look, for example, let's consider standard model backgrounds to supersymmetry in final states with jets plus missing energy. That's the canonical final state in which you produce gluinos, and the gluinos decays through cascades of quarks, charginos, neutralinos, and at the end of the day, it's just jets and missing energy taken away by the neutralinos. So there is what we call irreducible backgrounds. This is what was in the previous slide, for example, the real production of the W. So these are events that they cannot be distinguished from the signal on an event-by-event basis, given the amount of information that's available, of course. An example of a final state from supersymmetry where we have 4 jets plus missing ET is the production of a Z boson and 4 jets, where the Z goes to neutrino, antineutrino. There will be unavoidably a missing energy signal. Even if we could reconstruct the full event, we would know that this missing energy is not a single neutrino. There is some mass, because it's the mass of a neutrino, antineutrino, and certainly there is no way on an event-by-event basis that one can tell the difference between these and a real SUSY signal. But then there are also the so-called reducible backgrounds, and these are similar to what I discussed earlier, which was the CC bar way of producing the dilepton pair. Here, individual events feature properties which distinguish them from the signal. However, we can exploit these properties only with limited efficiency. For example, let's take W plus 3 jets. The W goes to a tau neutrino. The tau neutrino decays to hadron, the tau lepton decays to hadrons, plus, of course, a neutrino. Of course, this will be a very, very narrow beam of hadrons, but still it will be a jet. Experimentally, it will appear, this will be pions, a bunch of pions coming out. So now we have 1 plus 3, 4 jets, and we have the missing energy, which is a combination between the missing energy carried by the neutrino coming from the W decay and the one present in the tau decay. So this again, it's a 4 jet plus missing ET. Now here we could, statistically or in general, we could, if we had a perfect detector, tell these events as being backgrounds, because for instance, we would see these hadrons as coming from a secondary vertex because the tau lives for a finite lifetime, which is long enough to see the secondary vertex. And then we could also try to do the invariant mass of these hadrons and see that it's a number which is less than 2 GeV, so it's consistent with being a tau. We could have events like W plus 4 jets, where the W go into electron and neutrino, the electron and neutrino are emitted at very large angle. They go down the beam pipe, they're not seen, or they are very soft, and therefore, we don't count them. So again, electron and muon in general can be detected, so this background we can throw away by asking that there is no additional lepton, but occasionally we will not be able to detect them, and therefore that event will stay in as a background. And there is a whole collection of possible final states that you can come up with. And then finally, there is instrumental backgrounds in which, if you just look at face value of the event that's being created, it doesn't resemble the signal at all, but there is some failure of a detector that makes it appear like a signal. And in this case, for example, it's multi-jet. So there is no missing ET. One just produce a multi-jet final state, but then the measurement of the energy of these jets is not infinitely precise. There is a finite resolution, and therefore occasionally, by just taking the sum of all of the transverse energies, the vector sum, there is a residual which is missing transverse energy. And the point is that if we look at rate, so you take just the invariant mass of a final state, including jets from QCD, this is the rate as a function of this mass. If you do it for a SUSY signal, this is the distribution you get. So you see that down here, we are off by many orders of magnitude, so it's enough that your detector is inaccurate to 1 part in a million in properly reconstructing the energies of the jets, in developing far tails in missing energy, that you can easily fake a SUSY signal. Okay, so this is just an overview, more or less, of what we mean by backgrounds, what's the origin of these backgrounds. And I gave you those first few slides in which I indicated to you that in general, it's more than calculating backgrounds, which is necessary in order to decode and extract information from hadron collisions. So to really successfully search for BSM phenomena and to analyze them, the real crucial point is to understand what are the properties of final states in hadronic collisions. For example, what happens to the quarks that are generated when the gluino decays? How do they develop into physical observables, into jets? How different parts of the event talk to each other? And the goal of my lectures, therefore, is really to, rather than focusing on signal by signal, giving you the list of the backgrounds and calculating those backgrounds, will be in explaining to you what are the key ideas and the techniques that are used in the modeling of hard processes produced in high-energy hadronic collisions. And I say hard processes, meaning I'm not going to cover everything that happens when 2 protons come together. Most of the times when 2 protons come together, the result of a collision is a relatively boring final state. It's not particularly interesting. It's low PT scattering, low PT phenomena, which are not in the realm of perturbative QCD, even though the proton-proton energy in the center of mass is very large. But by having large impact parameter in the collision, the momentum exchange is actually small, and therefore we are mostly dealing with non-perturbative aspects of proton physics, which on one side are very hard to describe from first principles, and on the other, they have no impact on the searches for BSM, so I will leave that out. I think that one of the key questions that should be, the one thing that you should think of is that every time we have one of these hard processes, in the final state, we are going to end up with hundreds of particles, right? So this is a classical example of a final state of a proton-proton collision. Each of these tracks, I think it's a real event. It's not a Monte Carlo because there is a number, there is a time, there is everything. So this is a standard event, and it's only one event because it's 2010. The luminosity was very low, so there was, this is only one event. And you see, each of these tracks is like a pion, a kaon, a proton, something coming out. How can one possibly hope to provide an accurate description of a system in which there are hundreds of particles? I mean, typically when facing objects like these, we switch over to thermodynamics, right? And the question is whether 100 is large enough that we can study it thermodynamically, but certainly here thermodynamics doesn't work because it's not a process in which we can either thermalize or we can, conceive a statistical treatment, number one. Number two, the essence here is precisely fluctuations. We may imagine a way in which we can build a statistical mechanics to describe these final states, but the whole point of the search for BSM is that we are looking for far tail. We are looking for exceptions, for events which are very weird. And therefore, we cannot rely on such a generic treatment. We really have to rely on our ability to describe these far tails, these odd and weird configurations in which some features emerge that make these events look interesting. You cannot calculate a matrix element for proton-proton going to 150 particles, right? Think of a number of Feynman diagrams that would be involved. And anything that were to build a sort of a sequential approach, namely I start generating a W, the W decays to 2 quarks, and each quark starts radiating. Well, that is almost like a classical treatment because I'm talking about a sequence in time. And that means that I'm dealing with the different components of a hard process irrespectively of what's happening on the rest of the events. So where are all of the quantum mechanical correlations between what happens here now and what was happening there, few nanoseconds ago? Where are all of these quantum correlations gone? How can I cope without having to deal explicitly with the amplitudes, including every single object? These are the questions that have to be addressed. And fortunately, of course, there is a framework in which all of this is understood and that makes it possible to analyze such complex final states. So let me start from a very simple kindergarten-like picture of a structure of a proton. The proton, also Nima just said it a few minutes ago, well, it's not just a U and a down quark, but there is gluons being exchanged, at least because gluons have to be exchanged in order to keep the proton together. And if we look at short and shorter time scales, if we take an image of a proton with a very, very sharp time resolution, we can certainly detect also virtual fluctuations which are there simply because the proton is a quantum mechanical object like anything else. And therefore, one of these gluons that are being emitted in order to keep 2 quarks together can also split, for example, into a QQ-bar pair. Now, if nothing happens, if the proton is by itself, this object has to go back to itself and back here, because we cannot maintain such a high virtuality fluctuation alive for a long time. But if this amount of time is short enough, here, for example, we can put not just a UU bar pair, but we could also put a pair of bottom quarks or top quarks. The top quark is much heavier than the proton, but if we look at a very, very short time scale, there will be fluctuations inside the proton in which we excite top pairs. So we can think of reactions in proton-proton collisions as follows. We can really think of a single proton and all of the possible histories of what happens inside the proton as we look at them with shorter and shorter time scales. And since the proton contains a multitude of different objects to start with, up quarks, down quarks, as well as gluons, it has access to a huge multitude of possible intermediate virtual states. For example, one of these quarks can emit a virtual Z boson. It can emit a virtual gluon, and this gluon can go into a virtual TT bar pair, which can then go to a gluon and a Higgs. Of course, these will have to be virtual, right? There is no way I can keep alive such a fluctuation for a long amount of time, because I need at least a couple of 100 GeV to do that, but you know, the proton is 1 GeV, so it's not even such an immensely small amount of time. Again, I can emit gluons, and these gluons can go into an open TT bar pair. So I take a picture at any given time, and inside the proton I find all of these. And when I bring another proton in, I bring a probe, I bring the way in which I can project some of these intermediate virtual states into a real state. I bring in the energy that's missing. For example, I may come in with a proton, and this proton, one of its gluons can go hit this top quark. Let's say that when this gluon was produced, this gluon put a T-bar, which was on shell, and now this top quark, in order to preserve energy momentum conservation, was off shell, had a very, very large negative mass squared, but at this point it's enough to put in some energy in order to put it back on shell. And this energy is coming from this gluon. So this gluon comes in, it's going to put the top on shell, the T-bar was already on shell. So this system of the T and the T-bar is on shell, and it's not going to be touched, it's going to stay there. It will be a physical object. Of course, everything else now has to wrap it up before time expires, because nothing else is happening at this point. So everything else has to go back to where it was, to where it came from. Of course, it can benefit from the presence of the other proton, because this other proton, by definition, has to be very close in impact parameter relative to this proton, because otherwise that gluon would have never been able to detect the top quark that was off shell on a time scale of 10 to the minus 25, 26 seconds, right? So the two protons are really overlapping with each other for that to be possible. And of course, so that means that occasionally some other gluon or quark from here could also put on shell some of these other processes. One can have what is called double parton interactions, in which two partons from the proton interact from two partons from the other proton, giving rise to independent hard processes. But generically, otherwise, you know, this whole mess will have to settle into a possible equally physical final state in order to allow the T and the T-bar to come out free. And the result is that a lot of these particles will be liberated. When I come in and I project a component of a proton wave function onto the mass shell, everything else will have to rearrange and will give rise to these large multiplicity final states. Other things that can happen, of course, here I could have emitted a on-shell Z, leaving a highly space-like off-shell with negative mass square quark, and I take a quark from the proton coming in, or an anti-quark, annihilate this one, and then the Z is free. Or I can intersect the gluon in the graph below, and of course then I would have PP going to Higgs through the usual glue-glue through the triangle. So one can look at hard processes in PP collisions as looking at the history, all of the possible history of the evolution of an individual proton seen at different time resolutions, with the intervention of an external probe that occasionally comes in and manages to put a state on shell and let it become physical. Now, this is the physical picture. The mathematical picture that is being used relies on what is called the factorization theorem, which is the separation between, instead of looking at all of those possible histories explicitly, we just look at the possible histories of the fundamental building blocks of a proton, namely the light quarks and the gluons. And then we consider interactions between the light quarks and the gluons of one proton with the light quarks and the gluons of the other proton. And we deal with the direct production of a W, of a Z, of a TT bar pair by describing directly the matrix element between these two light components and the final state. And the factorization expression tells us that we can describe any given final state, hadronic final state X, by convoluting. This is the same expression that Nima wrote in his lecture. It's convoluting the cross section for the production of a partonic final state X hat, which could be, for example, quark-quark scattering to quark-quark, or quark anti-quark scattering into a W, convoluted with functions that describe the density of initial state light partons inside the proton carrying a fixed given momentum fraction of a proton momentum. So this function is called f of x. There is a variable q, which I will discuss shortly, which refers to the scale, the hard scale of the process. It's the time resolution at which I'm looking at this process. And then all of this is convoluted with the evolution of a final state. So I have a history in the initial state. The proton does all of its virtual things, and at a given time I can find gluons or quarks carrying a given fraction of a momenta. That some of their histories feeds into defining these parton distribution functions, which again are the density of quarks or gluons of a given type carrying a momentum fraction x of a proton plus everything else. We're not asking any other question about the proton. We're just singling out an individual component, parton of a proton. What happens to the rest of the proton, all of its possible other virtual excitations, we don't care. They will unitarily, namely with probability 1, they will evolve into something the moment I pick up this quark, and therefore I don't care about what they are doing. And then I have a similar sum of the histories of the final states, in which I consider all of the possible final states that take me from the given partonic final state that was created in the hard collision, projected into the physical observable final state, which I'm interested in. This could be, for example, this transition function could be a fragmentation function, namely I could be interested in B mesons. So I start from the production of a B quark, and then I make a convolution with a function that describes what is the spectrum of B mesons that arise from the evolution of a B quark. Or it could be something that projects the energy of this parton onto the energy of all of the particles contained within a given cone, a so-called jet algorithm. The quark evolving will emit gluons. I draw a cone, only a fraction of these final state particles will be included. That is my physical observable, and this F could be, for example, a jet algorithm. So this is the picture, and as you see, it's inconsistent quantum mechanically, because the separation between the histories of the initial state, the histories of the final state, and then just this interface is fully neglecting what happens when the history of the final state and of the initial state talk to each other. In the language of Feynman diagrams, I can have a gluon here emitted and then reabsorbed by the final state. So what is happening to these quantum mechanical corrections? They seem to be not included in this picture. So the answer is the following. On one side, the very short wavelength contributions, for example, a virtual gluon being exchanged between here and here, in order for this to happen and to have and to be relevant, has to happen over a very short time scale, because this by definition is a very hard process. So if I want this gluon to interact with, emitted from the initial state, to interact with the final state, it must do so in a very short amount of time, comparable with the hardness of a process. Okay? So here we're dealing with very, very large Q-square virtual exchanges, which can be incorporated in a perturbative redefinition of the hard matrix elements. In other words, I take the matrix element not at the leading order, at the Born level, but I take it at one loop in QCD. Gluons that have a longer wavelength, a longer time scale, will have been emitted far in the past, you know, they don't manage to get back and to interact with these final state quarks because they have a much longer time scale. So they still can do so, but then one can prove that their impact is suppressed by inverse powers of Q square. Okay? If little q square is their virtuality and big Q square is the hard scale of a process, one can prove that little q square divided by large Q square is the correction induced by the presence of these long wavelength excitations being exchanged between the initial and the final state. To the extent that we're dealing with very large Q square processes, these are so-called power suppressed effects. We neglect them because they fall below the accuracy of our calculations anyway, and we're only dealing with the leading perturbative contributions, which are typically logarithmic of powers of logs, and it's within this degree of approximation, namely the neglect of power corrections, where the factorization theorem is supposed to apply. So let me give an intuitive picture of why this scheme works. I called it a theorem. It's proven as a rigorous mathematical theorem for a class of processes, for example, production of W's and Z's. It doesn't hold for several other processes, for example, production of exclusive final states like charmonium or quarkonium states. And for other processes like jet production, one has to be very careful in the way one defines the final state in order to have factorization theorem to hold. But this is the basic picture of what happens. So let's look at a proton and look at what happens inside the proton. And we consider the exchange of gluons that are holding the proton together. And you know, we exchange a gluon here. The gluon will have to be reabsorbed because otherwise there will be some transverse momentum induced between these two quarks. We're interested in the exchange of hard gluons among the quarks. So if we have a hard gluon being exchanged, there has to be another one being reabsorbed. Otherwise, as I said, the thing just breaks apart. And it cannot break apart because there is nothing else from the outside. The proton is a stable object. So the effect of these hard gluons we can summarize by calculating this diagram, and that's an integral from Q to infinity. Let's say that Q is the scale above which I consider the hardness of the gluons. I have a loop integration. I have at least 6 powers of momenta in the denominator, 2, 4, 5, 6. So the integral from Q to infinity goes like 1 over Q squared. Now, of course, to make it dimensionless, and this is true because of asymptotic freedom, right? Because as I take the momentum to infinity, I don't have to bother about what happens to the coupling here, because I know that it goes very slowly, or it goes to 0, it stays constant. If I had a theory, not a gauge theory, other theories in which the coupling grows as a function of Q squared, of course, I would not be allowed to draw these conclusions. So here asymptotic freedom is crucial. So the net result is that if I want to look at it in terms of probability that hard gluons above a given scale Q contribute to holding the proton together, or their contribution to the proton wave function, or you name it, we see that the effect is of order m squared over Q squared. The proton mass is the only other dimensional parameter I have in the problem, or lambda QCD, but pretty much within a factor of 2, it's the same. Okay? So hard gluons, the contribution of hard gluons to holding the proton together is very, very small. And that means that the proton is held together by the exchange of gluons whose typical time scale is of order of 1 over the proton mass. So this ratio MP over Q has to be of order 1 for this gluon exchange to play a role. So it's long time scales, especially because that's true in the proton rest frame. If I have a proton of the LHC that's traveling, I multiply this by gamma. So the time scale for the exchange of gluons that are holding the proton together is of order gamma divided by the proton mass. And that means that if I come inside the proton with an external probe, and this probe has a virtuality which is much larger than the proton mass, that means that it has a very, very short amount of time to interact, the system has a short amount of time to settle, to react to this external probe. And that means that the individual quarks don't have time to negotiate with the external probe their reaction. They cannot talk to each other and discuss the problem of, this guy is coming, what do we do? Each of them has to take care of it by themselves. It's like, a missile coming and striking your building. I mean, there is no point in calling up your neighbor upstairs. What do we do, right? You better rush downstairs yourself and hope for the best for your neighbor upstairs. And here it's pretty much exactly the same thing, right? I have this thing coming in with 10 GV inverse or 100 GV inverse. There is no point in you sending a screaming signal to the other quarks saying, this is coming, let's hold together so that we can respond and bounce off as a proton. It will be the individual quark that's going to have to interact with it and to bear the consequences, namely flying off, recoiling, and the rest of the system will have to adapt. So the quark that would be struck by being hit receives no feedback from the other quarks. There is no way that the other quarks can do anything and acts as a free particle. So this is the basis of the Parton model approach to hard collisions. That's what makes it possible for us to consider and to work with quarks inside the proton as if they were free objects when we are discussing very hard probes. So, as a result, by definition, when we have a hard probe, we can just forget about the rest of the proton for the time being and look at the interaction between the external probe Q and a single parton. So let's see what happens if we start applying QCD corrections to this process. Well, one can imagine having a virtual gluon, as the quark comes in, of course, it had its history. So it had emitted gluons before. There was a whole series of virtual states that could have been present at the time. Some of these virtual states included gluons with virtuality Q larger than the virtuality of external probe. So their time scale for survival is even shorter than the time scale of external probe. So they have time to be reabsorbed. And that before the object strikes. So on one side, we're dealing with processes with a scale which is even bigger than the scale of external probe. So that means that they're calculable in perturbative QCD. So we can do the calculation. Alpha strong is small. It's a loop diagram. We know how to do it. It's like a wave function renormalization. On the other, as you see, they do not affect the momentum fraction carried by the quark, because if a gluon is reabsorbed, then the momentum fraction of a quark here or the quark before was exactly the same. So they really have absolutely no impact. It's a bit like a wave function renormalization. On the other hand, if we look at other components of this set of intermediate states, virtual states, the component in which this gluon has a virtuality which is smaller than capital Q, these have a long lifetime, and as I was saying before, the moment the external probe comes in, when they decide that it's time to go back because their life has expired, the uncertainty principle forces them to go back on shell, then they cannot find the quark any longer, right, because the quark is gone. So they are lost. And of course, at that point, they will have to find their way home in different ways, but they're gone. And they introduce two problems. The first one is that, you see, they carry away momentum. So when the quark is hit now, it has smaller momentum than it had before because they took it away. So it's important to understand how big, to understand these effects, because they do affect the density of quarks, the distribution of density of quarks carrying a given fraction of a momentum. And on the other, since Q now is below Q, when we integrate over all of these possible emissions, we go down all the way to Q to 0, namely gluons that have been emitted very far in the past, for example. But when we go to Q to 0, that's a domain in which QCD is not perturbative any longer. It becomes non-perturbative, alpha S becomes large. So then we're stuck because we cannot calculate them. So the previous ones, they were irrelevant and calculable. These ones are relevant and uncalculable, so we have a problem. On the other hand, precisely the fact that they were emitted long before the interaction, and they have a low virtuality, means that their emission properties do not depend on the interaction with a hard probe. So the fact that here at some point the quark, as the proton sits around, emits gluons and reabsorbs gluons, is independent of the fact that occasionally the proton could be hit by a cosmic ray and produce a W. It's just part of the internal wave function of a proton, right? If you wish. So that means that their properties are universal. They are independent of the hard process I'm going to consider. And if I find a way in which I can model them, either calculate them or measure them experimentally, then I can use this knowledge to simply make calculations. They will have an impact. They will define, in fact, what the quark density is. And I may not be able to calculate this from first principles, but I can do measurements. I can do a measurement of the interactions with an external probe, for example, a photon, deep inelastic scattering, electron, proton going to electron plus X. I parameterize the result of this process in terms of a partonic density f of X that will include, by definition, the effect of all of these gluons. And from the comparison between the measurement and my theoretical calculation, done, of course, under the assumption the factorization holds, so that I do have a framework in which I can calculate. Out of this comparison, I extract f of X, and then I use it in order to calculate any other process I'm interested in. And this is what justifies, if you wish, this universality of f of X, the fact that these parton density functions have labels indicating whether it's an up quark, a down quark, or a gluon, but they don't have a label saying this is what you should use in Drellian, or this is what you should use when you produce a Higgs boson. So they are universal, but there is a subtle thing in the whole reasoning, and that is that I define hard and I have this scale, capital Q, which is the external probe, and it's that scale that defines which ones are reabsorbed and which ones are not, and I have to deal with, right? So what is the role of this external scale, which a priori could be arbitrary? Let's consider then, again, our drawing. We have our quark. We have the interaction with a probe at a scale Q. I consider the impact of the emission of a virtual gluon with the scale mu, which is larger than Q it gets reabsorbed before the collision. So it doesn't have any impact on my parton density. However, if I instead choose a probe that has a virtuality which is larger than mu, then this comes in, and this gluon does not manage to get absorbed in time. So my quark will lose momentum, and therefore F, the parton densities, will be different. So I have to account for this apparent paradox that the parton density is not well defined, because depending on the scale Q at which I probe my system, I end up seeing a different parton density. But that's exactly what we expect, because we are probing the proton at a different resolution. If we are probing it at a different resolution, we are going to detect a different final state. But now you see it's relatively straightforward to go from the parton density. So that means that the parton density will have to carry not only x as a variable, but also the energy of the process at which I will be applying it. It's the resolution at which I'm looking at the proton. It's not enough to ask how many gluons carry 30% of a proton. You have to tell me, the real question is how many gluons carry 30% of the momentum of a proton in a process if I look at the proton with a resolution of 100 GeV inverse, 1000 GeV inverse, or 10 GeV inverse. And what is interesting is that all of these functions are related by a trivial relation. So it's not like it's an infinite set of functions that I have to go out and measure. It's enough to measure these functions at a given scale, and then I can transport them at different scales by just doing some simple mathematical evaluation, which is what I'm going to describe now. And the reason is that you saw the nature, the origin of the difference between the parton density F as I vary the scale. If I have a scale which is below this scale mu, then this gluon does not contribute, does not change f of x. If the scale is bigger, it will change f of x. And the change in f of x is simply having lost a given amount of momentum carried away by the gluon. So I can describe the relation between the parton density at a scale mu and the parton density at a scale q by simply applying the principle of detail balance. It's just a matter of having a gluon being emitted between the scale mu and q and carrying away some fraction of momentum. So the difference between these two is obtained by integrating over the quark density with a momentum fraction x larger, x in larger than x, because in order for the quark to carry momentum fraction x even after it has emitted radiation, it must have had a larger momentum fraction before, so x in larger than x, and I integrate. And then I integrate over the phase space in q squared between mu and q for the emission of gluons, taking away a momentum fraction which is exactly equal to such that after the irradiation, the quark is left with momentum fraction x, okay? So x in has to be equal to x divided by y, and that is enforced by this delta function. So this is kinematics, and all of the dynamics is into a function p that simply describes what's the probability that a gluon is emitted here at that scale and carrying the given amount of momentum fraction. And this is something for which we have to do the calculation. If it's QCD or if it's lambda phi to the sixth, it will be different theories, and therefore here we have a different probability, but everything else is simply pure kinematics. It's chemistry, right? So we write this equation again in the next slide. We solve it, and you can do this as an exercise. And at the end of the day, what you can prove is that from there, you obtain that the derivative, the logarithmic derivative with respect to the scale of the parton density is proportional to the convolution of the parton density times these so-called splitting functions, namely these functions that describe the probability of emitting a gluon with a given momentum fraction, times alpha s over 2 pi, alpha s, of course, because the emission of a gluon costs alpha s. So this is an integral differential equation that is a self-consistency equation for the partonic densities that has to be satisfied in order for the system to be consistent. This consistently describes the evolution with resolution of the density of quarks or gluons inside the proton. Now, we consider the possibility of a quark being hit and radiating off in the process. But other things could have happened. For example, I could have considered a higher order virtual process in which the quark emits a gluon, and if a gluon has enough time, it can itself split again into a quark-anti-quark pair. And when the external probe comes in, instead of hitting the quark that I had there to start with, hits the quark that was radiated off from the gluon. So this is an additional contribution to the evolution equation of the quark density. This is what we just wrote down in the previous slide, proportional to the quark times the probability that the quark maintains its energy emitting a gluon. Here, this is proportional to, well, if we assume that we can describe even this gluon with its own density inside the proton, we may as well put this directly proportional to the density of gluons inside the proton times the probability that the quark arises from a gluon carrying this momentum fraction. If my external probe is a gluon, not only the gluon interacts with quarks, but the gluon can also interact against gluons. And for a process like this, I do need to know how many gluons there are in addition to how many quarks there are. And the evolution of the gluon density is related to gluons, which then radiate gluons and get dispersed when the probe comes in. And there are contributions from now quarks emitting gluons. So there are all of the possible little histories, all of the little building blocks in all of the possible histories of a proton evolution will contribute. And each of them, of course, will have exactly the same structure, with the difference that these kernels, these splitting functions have to be explicitly calculated, and I just gave them to you here explicitly in case you ever want to use them. And you can also try to calculate some of them because in principle using relatively simple techniques that can be done. Sorry?
Why are the splitting functions calculable in perturbative history? You wrote that down in the last slide.
Yes, these things are calculable in perturbative UCD. Because why is that? Yeah, they're calculable because these are really transitions between a quark, and a gluon. Sorry, they describe here, right? A quark, and a gluon. So the external state, and this is a free quark. It's not. All of the non-perturbative part is built into the boundary condition. I have this, let me go back to the previous equation, which was, it's exactly like this, but it's a bit simpler. So this is the equation that controls the evolution of a parton density. The differential equation tells you what happens locally in Q square as I change the scale. And what happens locally when I change the square is physics that takes place, when I change the scale, is physics that takes place at the large scale, because I'm dealing with scales which by definition, by construction, are large. I'm interested in a probe coming in at a large scale. A scale large means much larger than lambda QCD, okay? And that differential equation tells me what's the difference between moving slightly around, taking a large scale and looking at how the quark density changes if the probe comes in at this scale or comes in at that scale. So it's local in Q square, if you wish, and it's all taking place at large Q square. So I can work with quarks and gluons as being perturbative objects, because that's what all it boils down to. What is non-perturbative is the status at t equals to minus infinity at very, very low q square, where I'm coming from. That's the part that I cannot deal with perturbatively, okay? So the whole point is to go out, do a measurement at a given fixed scale, which is large enough that I can apply the factorization theorem, and I can apply the theoretical, a perturbative calculation of a matrix element, and I make a prediction as a function of an arbitrary parton density f. Arbitrary means I can write it down as a sum of an infinite set of orthogonal polynomials, for instance, as a closed set of functions with support between 0 and 1. And then I go and I fit this data. And by fitting the data, I extract the functional form of f at a given scale, let's say 10 GeV. And once I have it at 10 GeV, at that point, I can apply those equations, the Altarelli-Parisi equations, to bring it up to 100 GeV, 150 GeV, 300 GeV. And I have all I need to do physics at scales above that 10 GeV, of course. All of the non-perturbative information is collected and absorbed by the partonic density, which I cannot calculate from first. I mean, in principle, I could do it with a lattice, but nobody has been able to do it so far in a compelling way, in a way that is useful for phenomenology. So as I said, I will keep it a bit shorter today, but just give me 2 minutes to show you one plot, something that Nima already promised you I would show, so I cannot not show it because otherwise you guys want your money back. So these are examples of these PDFs, parton density functions, how they evolve, how, what's their behavior. What I have here is the valence up quark. The valence quarks means the quarks that are there somehow to give quantum numbers to the proton. And these are the quarks that carry most of the momentum fraction. If we go to very, very low q square, you can imagine that if you look at the proton with very, very loose resolution, you will not see many of these quarks emitting gluons that emit quarks, etc., because at low resolution you don't have you don't have a very sharp time window that allows you to stimulate these highly virtual off-shell states. So you're down to a very basic picture of a proton in which there is 3 quarks and few gluons around. So these quarks, the valence up quark, as a function of a momentum fraction, 1, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, you see they carry on average between 20 and 30% of a proton momentum. That's the up quark, and there is 2 of them. So the down quark will be a slightly less, like half of it. So 30% plus 15, that's about 50% of a proton momentum is carried by valence up and down quarks. The other 50% of a proton momentum is carried by gluons, something that presumably you heard because it's historical. At the very beginning, as soon as at SLAC with electron scattering, people started decoding the results of the measurements in terms of a partonic structure of a proton. People realized that quarks, charged objects, only accounted for half the momentum of a proton. Now, this solid line is the f of the up quark at a scale of 3 GeV. And from there, and that is a result, as I said, of a comparison with a measurement, we now evolve using those Altarelli-Parisi DGLAP equations up to higher momentum to 10 GeV, 100 GeV, and you see that the shapes change. Typically what happens is that it becomes softer. You get fewer and fewer quarks carrying a large amount of momentum, and you get more and more quarks carrying less momentum. And the reason is simply that as I go to higher virtualities, more and more, some of these gluons that were emitted don't make it to be reabsorbed. So if I probe the proton at a shorter time scale, I find more often I will find a naked quark, a quark that has given off some of its energy to one of these virtual states. So it's reasonable that their spectrum moves from being hard to being softer. The integral of these curves always has to be equal to 2 for the up quark, because there is 2 up quarks in the proton, and 1 for the down quark, because there is 1 valence quark in the proton. Here is the distribution of the gluon. And as you see, the gluon also tends to be, there is an important contribution even up to large x. This is x times the gluon density. Likewise, this is x times the quark densities. So if this distribution at small x were flat, then it would mean that the gluon density goes like 1 over x. And 1 over x is what you would expect, for example, if it were photons inside an electron, as opposed to being gluons inside the quarks. That's the Bremsstrahlung spectrum of photons in QED. That's typical of a gauge theory. It's true in QCD as well, but in QCD, not only quarks can emit gluons, but also gluons can emit gluons. So, in other words, the gluon has more opportunities to lose its momentum, to degrade its momentum, and to become softer than the photon inside an electron. And that's why the distribution of gluons at small x, gluons carrying a very small fraction of a proton momentum, increases more than 1 over x. And again, the same phenomenon. It becomes softer and softer as the scale becomes bigger and bigger. And if we put everything together, that's the C. These are the C quarks. C quarks are the quarks that come from, they're not the valence quarks, but it's the quarks that come from a gluon that splits into a QQ-bar pair. So up quark and anti-up quarks in the C have practically the same distribution. And you see that their spectrum follows very closely the spectrum of a gluon. And the reason is simple, because they come from a gluon that splits into QQ bar. And since they come from a gluon that splits into QQ bar, that means that to go from the gluon to these C quarks, there is an extra alpha S. And that means that on average, you would expect the C quarks to have a density which is about 10% of the gluon density. And if we look at numbers here, that's pretty much what we see. You see at 10 to the minus 4, we have a density of 1, while in the case of a gluon at 10 to the minus 4, we have a density of a bit more than 10, 15. So the ratio is exactly alpha S. And that is reflected also as we go up in scale. And if we put everything onto the same plot, on the same scale, and we do it at 1 TeV, which is the typical hard scale of the interesting phenomena at the LHC, we see the following. So this is now absolutely normalized. And you see that up to x of the order of a bit over 0.1, the most likely object that you find inside the proton is a valence quark, an up quark. If we go below 0.1, the most likely object you will find is a gluon. And there is 10 times more gluons than there are quarks or antiquarks inside the proton as we go to x, which are smaller and smaller. These lines are, the C quarks, so quarks or antiquarks. The dashed line corresponds to an up quark. The dotted line corresponds to the charm. So the charm quark is much heavier than the proton. If you go at very low Q square, if you look at a proton with a resolution of 1 GeV, like the proton in atomic physics or in nuclear physics, there is no way you can see a charm inside it. But as we go with a resolution which is larger than 1 GeV, of course, CC bar pair, virtual CC bar pair starts popping up. And when we go up to 1 TeV, you see 1 TeV is so large compared to the mass of a charm that inside the proton at 1 TeV, pretty much there is no difference between a charm or an up quark. And in fact, we find almost as many charm quarks as there are up quarks at that scale. This is clearly very important when we do calculations for backgrounds, etc., because you would assume that the charm process will be very much suppressed relative to the others. It's true if you're looking at charm production at threshold, but if we are looking at a 1 TeV process, the charm quark is as likely as being around as light quarks. Okay, so I promised that I would stop by 12:45, which it is. So I stop here and